Hello, everyone, and thank you for having me here today. A big part of being a researcher is to communicate the research and the knowledge to not only the other scientists, other researchers, but also to actually the groups that we are doing studies on, and that will usually that will hopefully put all of this knowledge into action. And so I'm very pleased to be able to present for the stakeholders here, which are you as athletes, and as well the organizers of these events. So the topic of my talk is how can a long distance triathlon affect a lung function? So here we go. So the talk today, I will start by giving a short introduction to respiratory physiology. I will give some background for this study, and then I will go through the methods and the results and a bit of a discussion before I will talk about some future studies and finally some take-home messages. So the respiratory system consists of the lungs and airways, and the purpose of the respiratory systems is ventilation and gas exchange. So the airways will lead air from the surroundings down to the alveoli in the lungs, where the gas exchange occur, meaning that oxygen will go from the lungs and over in the blood, and carbon dioxide will go the other way around. So to transport the air from the surroundings and into your lungs, you have to use your respiratory muscles, as shown in this simple model up in the left-hand corner. And we mainly use our diaphragm, as shown here. And when that constricts, it will increase the volume of the lungs, and then the pressure will be reduced. Increase the volume of the lungs, and then the pressure will be reduced. And this will actually get the air to be sucked into the lungs from the surroundings. When the diaphragm relaxes, the volume will go down, the pressure will increase, and the air will go up again, out again. And this is what's called a ventilation. So when we're sitting here at rest, we will breathe about 5 to 10 liters of air every minute. But during exercise and heavy exercise, this will increase drastically. And in elite athletes, they can breathe almost 200 liters of air per minute during maximal exercise. So a lung function is a measure of how much air you can fit into your lungs, and as well as how fast and hard you can breathe out. And when we measure lung function, we do it using a method called spirometry, where you breathe through a device called a spirometer that will measure the flow of air and also the volume. And the results are shown in a flow volume curve, as shown here, with the volume on the horizontal line and the flow on the vertical line. And if you have a reduced airflow, you can get a U-shaped curve, as seen in the black curve here, and a normal lung function is shown as a red curve. So a bit about asthma. This is a disease characterized by a chronic inflammation in the lungs, and this will result in airflow limitation, as you can see in the photo, where the tubes and the respiratory tubes the diameter is reduced because of the inflammation and increased mucus production. And this will make it harder to breathe, and you will get respiratory symptoms such as shortness of breath, cough, and the wheezing breath. Exercise-induced bronchoconstriction is a term when you get a constriction of the bronchi of 10% or more after exercise. This is very normal in asthmatic persons, but also observed in non-asthmatic persons. Now I'm going to talk a bit about the background of this study, and we know that asthma in athletes is very common. In the regular population, there's about an 8 to 10% prevalence of asthma, but among athletes, depending on the level or the type of sport, you could get up to 50-60% prevalence of asthma. And the highest prevalence is observed within endurance sports, especially swimmers, and as well as winter sport. And the development of asthma in athletes are related to exercise intensity, training volume, how much you exercise, and the restitution, so the time between each training session. And this is because of the high ventilation that these athletes perform daily over many, many years, that will cause a damage to the airways that will give an inflammation. And if you exercise often enough or at high intensity very often for many years, then you can get this chronic inflammation in the lungs, which is asthma. In addition to this high ventilation, you will get an increased exposure to the environment when you breathe that much, that often. Especially if you get cold air and dry air, you could inhale particles from pollution, chlorine from swimming pools that will further be damaging to the airways. So there's not much evidence on the prevalence of asthma or exercise-induced bronchoconstriction in triathlons, but the potential is definitely there, being that you do endurance sports and also swimming, and also the competitions in a race such as Norseman is quite extreme, with the duration, the ventilatory demands during the race, and also the environmental factors. There's been some studies on the effect of ultramarathons and marathons and some triathlons, and they show that this will have effects on the lung function, but we do not have enough evidence that we can say for sure. So we simply have very little evidence on how such a race affects the lungs, and this is a critical organ, obviously, for all sport performances. So that's why we have been able to do research on the Norseman for some years now. And the lung part is not all the things that are done. This is a part of a larger study. We have, the research group have done measurements of core temperature, biomarkers from blood samples, and lung function, and even more. So we've been doing this for a couple of years now. And the design of this study is a cross-sectional design, meaning that we will only measure the participants at a short amount of time, and we do not follow them up over time. So the aim of this study is to examine the changes in lung function and oxygen saturation from before to after the race. We want to look at the prevalence of exercise-induced bronchoconstriction in Norseman participants. And finally, we want to look at the association between these changes in lung function and performance that we measure as race time. And what I'm presenting today are results from the races in 2016 and 17 combined. So here we did the exact same thing, but we, in these 2 years. So what we did was that we did measurements at baseline 1 or 2 days before the race. We were in the hotel at Eidfjord. And then we measured the participants again about 10 minutes after finish at Gaustatoppen, and some we did at Gaustablikk. And we did the final measurements the day after the race. And this is what we did. We measured lung function by spirometry, and we measured oxygen saturation by pulse oximetry. We measured blood pressure and heart rate. At baseline, we also measured body composition, and the participant completed a questionnaire regarding medical history, respiratory symptoms, and the use of medications, etc. So our participants, we had 63 we measured at baseline, and then we had 57 who completed all 3 tests, both at the finish and the day after. And the mean age was about 40 years. We had 13 women and 50 male. And they had the normal BMI, normal blood pressure, and quite impressive resting heart rate the day before the race. And here are the results. So here you see the 2 variables that we measure in the lung function, FEV1, which is the expiratory volume that you breathe out for 1 second during the test, and the vital capacity, FVC, of the total lungs. And then we can see here that in all participants, lung function is reduced from before to after the race in all participants, and even the next day they still had a mean reduced lung function. Almost 50% of the participants had a decrease of 10% or more, and this is defined as exercise-induced bronchoconstriction. 16 of these athletes still had a reduction of more than 10% the day after the race. We also found a significant reduction in oxygen saturation both immediately after the race and also the day after. So 65% had a more than 4% reduction, meaning that they fulfilled the criteria for mild to moderate exercise-induced arterial hypoxemia, which is often observed in elite athletes, as well as if you're at high altitudes. So, a bit of a discussion. Field testing is both a friend and a foe in sports sciences. It's very unexpected. We do not know when the participants will come to the Gaustatoppen. It's very difficult to plan, and it's very difficult to standardize, which is very important. But on the other hand, we cannot simulate actual race conditions in the lab. So to be able to do field testing is a must within sports science. So here you can see how it looks like, or it looked like at the top of Gaustatoppen, where we are doing blood samples, measurements of lung function, measurements of blood pressure, and people are buying waffles and trying to recover from the race. Some are tourists, some are competitors. It's quite chaotic, but still we managed to do it, and it's been a great fun for so many years. The mechanisms and why this happens is very difficult to explain, but we see that our results with this high prevalence of exercise-induced bronchoconstriction corresponds with previous studies on other athletes, as well as studies after long ultra marathons or marathons. One reason for the reduction in lung function could be that participants had an undiagnosed asthma. And very many reported different exercise-related symptoms, and cough being the most prevalent symptom. 4 of the participants had an asthma, but they did not show a reduction in lung function, probably because they used medications. Another reason could be that they had fatigue in the respiratory muscle, meaning that they could not be able to maintain the ventilation level required to meet the energy cost of the activity or the performance they would do. A third theory could be it was due to increased parasympathetic activity. This is shown to be increased in elite athletes and related to VO2 max, and also the parasympathetic nervous system is responsible for the bronchoconstriction. So an increased activity here could mean that the lungs would easily constrict. Finally, reduced lung function could be due to a pulmonary edema induced by exercise or swimming. This is a rare but very important cause of acute problems, respiratory problems in swimmers or athletes. But we do not know if this occurred in our athletes, but it could explain the reduced lung function. So what about performance? We did not see any relationship between the race time and the reduction in lung function. For example, it wasn't the participants with the shortest amount of who completed the race in the shortest amount of time who had the larger reduction in lung function. And this could maybe be explained that lung function and oxygen uptake are not completely the same. So many will think that these are the same, and oxygen uptake is obviously a very important character in endurance sports. But oxygen uptake consists of more than just the lungs. So we have the lungs, we have the heart, we have the blood, and we have the muscle. And all of these together will form the oxygen uptake. So if the lungs are reduced, then maybe other systems will compensate for this. In addition, we have quite large lungs. So even if our lungs are a bit reduced, we can still manage to keep up a sufficient oxygen uptake. So, future studies. We will soon start to recruit participants for our next project, and we want to further investigate not only the lungs, but the health implication of participating in long-distance triathlon. So we are eager to follow up athletes during their preparations for Norseman 2021, and we want to map the training volume, the injuries, and other health issues in the months before. And we also want to test their physical fitness, their VO2 max. At the Norseman 2021 race, we will further investigate changes in lung function, the respiratory muscle fatigue, and the parasympathetic activity to try to get a better understanding of these mechanisms. So finally, I have some take-home messages. We found that reduced lung function is common after the Norseman Triathlon, even in healthy athletes, but we need to know more about why. Both athletes, crew, and medical staff should be aware of pulmonary changes during these races, in particular in cold weather. And triathletes with respiratory symptoms should be thoroughly examined for EAB by a doctor prior to racing. And finally, I want to say a huge thank to the entire research crew. Research is never done alone. So here is the crew that will doing all the testing in 2019. I especially would like to thank Trine Stensrud, which is the head of the lung part of these studies, as well as a master student Camilla Ilidi, who also did a huge job doing all the lung function measurements. And finally, a huge thanks to all the participants. It's very impressive that so many were able to, when they focus on the race and after the race, they've been so tired that they still managed to meet at our appointments and do the measurements. I can only imagine how much that would have cost, but their contribution is so valuable and will help getting more knowledge about this very important topic. So thank you to all the participants. If you are interested in this topic, you could read this paper that we have published this year. So here you get the full reference, and thank you very much for your attention.